Hello, I'm Yanan from Tianjin University. I'll be talking about our work on INFless, a native serverless system for low-latency, high-throughput inference. Started from AWS Lambda service, which is released in 2014, serverless computing has been growing rapidly in recent years. In the year of 2019, a Berkeley report has predicted the development of serverless computing in next 10 years. Due to its resource management-free, auto-scaling, and cost-efficiency advantages, serverless computing has been a success in multiple areas. Machine learning inference is yet another promising area for serverless adoption. Inference services are often integrated into online websites and comes with strict latency requirements. For example, China's largest local life service website has deployed more than 600 machine learning inference models, serving millions of requests every minute. And 90% of the inference response times should be less than 200 milliseconds, as inference models always have complex computations. They are deployed in a hybrid CPU-GPU cluster for inference. Although prior works has proved the great potential of serverless inference, current commercially available serverless services such as Amazon Lambda, Google Cloud Functions do not cater to the needs of machine learning inference and cannot meet the low latency, high throughput demands of inference services. High latency. We characterize the invocation time of inference models on AWS Lambda under different function memory sizes, and find that even given the maximum function memory, large models will experience a long execution time. Batching is an optimization method specifically designed for machine learning inference, while batching makes the function performance become more even worse. The latency for some small-size models increases more than 4 times. Resource over-provisioning. Accelerators like GPU device is not supported in existing serverless platforms. They can only guarantee low latency by increasing the resource allocations and result in low resource efficiency. As shown in the figure, more than 50% of the function memory is over-provisioned for serving these models to meet the latency requirements. Low throughput. In existing serverless platforms, each inference request is dispatched to a separate instance. This one-to-one mapping policy causes low resource utilization, while batching could help to reduce much of the launched instances and resource usage. To improve the throughput, the state-of-art method builds another new buffer layer on top of the AWS Lambda, aggregating requests into batches before submitting them to serverless platform. But the two-layer design introduces additional scaling overhead and only brings limited system throughput improvement. Moreover, the end-to-end latency is still not be guaranteed. These observations inspire us to design a novel native serverless system for cost-efficient inference services. To achieve this goal, the serverless inference system should be able to support hybrid CPU and accelerators, produce resource efficiency scaling, and provide built-in batching mechanism. Besides, function profiles is also needed to explore more flexible instance configurations. A serverless inference platform should integrate the features of inference to optimize system performance. When compared with the OTP approach, the native design brings opportunities to improve the system performance from function scaling to resource management. There are several challenges need to be addressed. First, for each function, how to choose the optimal hardware and batch configurations to maximize system throughput is challenging. Additionally, the function scheduling delay, instance startup, and batch processing will impact the function performance. Guaranteeing the end-to-end latency is also a challenge. Finally, the newly added module or modification should be lightweighted and easy to use. The system running overhead should also be low to make it more practicable. Here we present our Infless design. Infless is positioned as a domain-specific serverless platform for easy and cost-efficient inference service development. It supports the GPU device allocation and batching mechanism, the function profiling module, non-uniform scaling engine, and code start manager are the main components of Infless. For developers, Infless provides function templates to help them easily build inference functions. When a function is deployed, Infless builds a performance prediction model and automatically manages the runtime functions, thus to provide SL guarantee for user queries. Infless adopts the built-in batching and non-uniform scaling policy to achieve high throughput. Instances of the same function may have different configuration, which enables flexible allocation of resources and workloads at the instance level. A user requests first within a batch queue until the batch is entirely filled or times out to guarantee the latency SL without dropping any requests. We also design a batch-aware workload dispatcher to restrict the request arrival rate toward each instance within a range of R-low and R-up, where R-low or R-up denotes the lower or upper bound of the workload that can be processed in one instance. For scaling, the auto-scaling engine monitors the overall workload and turns the instance configuration. To avoid frequent scaling oscillation under workload fluctuations, we allow each instance to have a varied workload which is controlled using a constant alpha. In practice, alpha is set to 0.8 in our implementation. To deploy as many instances as possible with limited resources, while guaranteeing the latency SLO, we design a prediction model to estimate the function performance under various batch sizes and resource configurations. As offline profiling every inference function is rather costly, we instead adopt a lightweight method. We find that inference functions share a common set of operators, and the execution time is dominated by a small set of them. Hence, we collect the operator profiles to build the function performance model. Given an operator OI, we define the function profile as a 5-tuple, including the input size, batch size, CPU quarters, GPU quarters, and execution time. Thus far, we have collected more than 100 operator profiles and stored them in an operator profile database. In the operator task graph, the overall execution time can be estimated through a combination of sequence chains and parallel branches. For sequence chain, the execution time of the chain equals to the sum of all its operators. For parallel branches, the overall execution time of the branches equals to the maximum time among all branches. The evaluation shows that the operator combination model achieves less than 10% of the average prediction error for different inference functions. A core component of Infless is the non-uniform scaling engine. When the function scaling events are triggered, the scheduler takes the inference model profiles and the cluster resource status as input, explores to determine instance configurations to maximize the resource efficiency under an SL guarantee. In order to guarantee the end-to-end latency of inference functions, we characterize the latency breakdown of one serving request inside the serverless platform, and find that the overall latency mainly consists of 3 parts: batch queuing, batch execution, and cold start. Thus, we must manage them accurately in the function scheduling to guarantee the latency SLO. The function scheduling can be defined as an optimization problem, denoted by m the number of available servers in the cluster. Suppose there are at most n instances to schedule. The objective is to minimize the CPU and GPU resources occupied by the instances. Equation 3 to 7 are the constraints of SLO, resource capacity, and workload respectively. This optimization problem is at least as hard as the known NP-hard bin packing problem. Therefore, we resort to a greedy scaling algorithm. As the batch size is one of the key components that contributes most to throughput, we always first explore the configurations with a larger batch size for each new instance. The algorithm iteratively checks whether the maximum batch size can be employed. Given a candidate batch size B, it first explores all possible resource configurations that meet the latency SLO. If there are no feasible configurations, it turns to the next largest batch size. Otherwise, it will select the resource configuration with maximum resource efficiency and launch it on a server. To reduce the number of cold starts, a state-of-art approach, hybrid histogram policy, tracks the request arrival intervals and dynamically pre-warn functions based on a histogram distribution, while it is costly to find an appropriate static duration for the short-term workload bursts. A long duration leads to a conservative pre-warming, resulting in resource waste, while a short duration will make the histogram not representative, leading to SL violations. We propose a long short-term histogram policy to address the problem. We track both the long-term and short-term histogram and determine the pre-warming and keep live windows using their weighted sum. Influx is implemented based on OpenFast with about 9,300 lines of code. The source code can be downloaded from GitHub. We evaluate Influx using two real-world applications in 58.com. These services are triggered by dynamic invocations using the production trace from the Azure function. Our test bed consists of a 8-server local cluster and large-scale simulations. We compare Influx with the recent batch and original OpenFast. When compared with OpenFast and batch, Influx can improve the throughput by 5 times and 2 times on average in both OSVT and QA robot scenarios, respectively. The components evaluation results show that each component of Influx contributes much to throughput improvement, with batching being the highest. The non-uniform scaling design enables Influx to explore flexible configurations on both batch size and resource allocations. Influx could choose different batch size when the workload and resource status changes, and reduce the provisioned resources by 60% compared with batch. Influx can guarantee the latency SL of Influx workloads under different SL settings. The SL violation rate by Influx is less than 3.1% on average, which is far lower than the baselines. To evaluate the effectiveness of the scaling algorithm, we further pass the instance configured by batch to the algorithm. We see that Influx generates a resource fragment ratio as low as 15%, which is much lower than the other. Influx scales well in large-scale evaluations, with the concurrent request scales to 10,000. Influx still achieves 2.8 times and 4.2 times higher throughput than batch and OpenFast. Influx can also help to reduce the cost of constructing inference services. Considering the 400 a server production cluster in 58.com with 1.9 billion requests per day. Influx could help it save about $1.2 million every year. The scheduler design in Influx is highly efficient. Scheduling a single instance takes only 0.5 milliseconds, while the concurrent resource scales to 10,000. The overall scheduling overhead is still less than 1 second. Influx is designed as a domain-specific serverless platform for Influx to solve this problem. We also hope this work can attract attention from the serverless computing researchers. Influx is just a start. We would like to further improve the system efficiency of serverless computing in the future. Thank you.